everybody. Welcome back to Bio229 Microbiology. I'm Mary Annarella, your host, and we are in the home stretch of this semester and course. Now, we have been talking about different types of immunity, and last time we talked about innate immunity, which is just your body's first line of defenses. We talked about skin, we talked about antimicrobial substances, and we talked about the normal flora. Where'd that go? There we go. Group of microbes that normally live on the body's surfaces. They're supposed to be there. They keep you healthy. And they do so by, they compete with pathogens by basically crowding them out so that they don't have room to set up shop, by crowding them out and by their not having food resources. And they also play a role in the human immune response as well. But as you read in the New York Times article, let me get back to Notability here. There's a whole lot else going on with the normal flora, and you'll be writing that up as well. But one thing that I do want to point out that really struck me was flora in breast milk. Produce very short, what we call oligosaccharides. These are very short carb pieces, very small sugars that humans can't digest. Why would you feed that to? Why would breast milk produce a sugar that the baby can't metabolize? So what the heck is up with that? These oligosaccharides actually feed microbes. Microbes are certain microbes. I'll just write that down. They feed certain microbes and encourage them to grow, right? If you don't feed something, it's not going to grow. If you feed a microbe, it's going to grow. And it feeds certain microbes of the flora. So it actually helps the baby's normal flora become established. That is just wild, really wild. Or rather, flora, it's not flora in the breast milk. I'm trying to remember. Flora in the mother's body produce oligosaccharides that get into human breast milk. I just found that absolutely fascinating. And another take-home message for that article, for me anyway, was that we're not just coexisting with our flora. Here's us, and let's say here's our flora all over us. This isn't a coexisting thing. This is a terrible analogy here. This is a mutually beneficial, symbiotic relationship that our flora and us, that we're in with our flora. We're in, hopefully, a very healthy, mutualistic relationship with our flora. It's like we are taking care of each other. Our flora takes care of us, and we have to take care of it. It's more like we're gardening, really. We're gardening on our bodies, and we need to take care of our flora. We don't want to upset it too much by, being on antibiotics 24/7, for example. That's not a great thing for us. So it's just to reiterate how important the flora is to human health. Just really fascinating. All right, so moving on, we've been in chapter 14. And I know I was saying and 15, but nope, actually we're really not doing chapter 15. My PowerPoints are a little out of date, and I got the chapters wrong on several of these. And, hang on, we're having technical difficulties here while I'm dealing with my little desk thingy. All right. So chapter 14 is innate immunity, innate immunity. which includes the flora, which includes natural antimicrobials that your body produces, which includes your skin. Chapter 15 is the adaptive response. And we actually are not covering this in microbiology. This is generally something that people get in their A&P courses. So, this is all about B cells, T cells, neutrophils, macrophiles, the entire immune response. So we actually are not doing chapter 15. But we are going to be doing applications of adaptive immunity. So just to quickly talk about adaptive immunity. I missed an M in there. There we go. Adaptive immunity is active. It's immunity that you get from an immune response. It's immunity that develops when an organism is presented with a pathogen. So in response to are keywords there. Immunity that an individual develops in response to the presence of a pathogen. And by pathogen, I mean any microbe that causes disease. Pathogen is basically any microbe that causes a disease. All pathogens are microbes, but not all microbes cause disease, so not all microbes are pathogens. So adaptive immunity is a learning. And it involves something just really, really basic. This is definitely not all of the immune response. But there are just a couple of words that I just need to make sure that you all know what they mean. And basically, we have the word antigen and the word antibody. All right, now if you look up the term antigen in the glossary of your book, it'll probably say like a molecule that specifically reacts with a specific antibody. A molecule on a pathogen that reacts with, or let's say binds to, a specific antibody. So if you're thinking, great, if I look up antibody, is it just going to say a molecule that reacts with or binds to a specific antigen? And well, kind of, yes. But an antibody is a protein that is produced in response to being an antigen. It's an immunoprotein. It's actually Y-shaped. It's an immunoprotein produced by the body, produced by an organism in response to an antigen. So what the heck does this all mean? Let's give ourselves a slightly alternate definition of antigen. An antigen is a molecule, usually on a pathogen, sometimes it's on your own cells if things go awry, that the immune system recognizes as not self. Not self meaning this isn't us, this is some little invader who's not supposed to be here, and it sets off a series of events, one of which is that will cause the immune system, will cause the B cells to basically construct antibodies to react with the antigen. So let's say Let's say we have our little coronavirus, and here's its spike protein. Everybody knows all about the spike proteins now. We're probably tired of seeing this stupid little drawing. But the spike protein is considered an antigen. And an infection of the coronavirus, so here I should put its little mRNA in there, will cause the immune system, will cause the B cells of the immune system to produce an antibody. Like I said, they're Y-shaped. Here we go. Like that. That will cross-react with it and bind to each other. So here's our antibody. I'm just going to put AB for antibody. AG is for antigen. And the antigen, the spike protein, will bind to an antibody like that. What that does is tag this virus so that other immune cells can find it. Now, oftentimes, and that's not always the case, and we don't know that it's the case with coronavirus, a lot of times your cells will simply always remember to make those antibodies, will remember how to make those antibodies. So that when you see it again, when you see the coronavirus again, chances are you wouldn't get sick. But we actually don't know how long the body is able to make these antibodies, how long they persist. Some have said up to 4 months and then there's no more immunity, and some said, well, maybe it could be years. We just don't know yet. But in cases like, the measles, for example, antibodies against the measles virus persist. And so your immune system will be able to fight off the measles virus should you see it again later in life. That kind of thing. So we just need to be familiar with these two words. Antigens are on the pathogen. Antibodies are made by your immune system, by the B cells. Sorry, drinking my tea here. All right. So these words are going to come up, so we need to know what they mean. But back to the PowerPoint, because there are some other concepts in immunity that we need to talk about. Oh, not the flora. Here we go. Different types of immunity. Natural versus artificial. Active versus passive. Let's talk about this, and I'll do a screenshot here. Okay, natural meaning happens all by itself. Happens without effort, right? Without much effort. An example of natural immunity would be what I was talking about. You're exposed to a virus, your immune system, you have an immune response, and your immune system makes antibodies against a particular pathogen, and those antibodies persist in your system. Next time you see that, next time you see that virus, your cells see that virus, it's going to tag it. You're not going to get sick from it. That's very natural. It's like catching a cold, catching the flu. You're not going to catch the same flu from the same virus twice. Artificial doesn't happen naturally. So, vaccines would be an example of this. So let's see. There is also active immunity versus passive. Okay, passive immunity is when, let's say, you get antibodies that were made by someone else's body. Antibodies made by somebody else's body protect you. So let's say you receive antibodies, ABS antibodies, that were made by someone, I can't spell, else's body. So can you think of an example of passive where you would receive antibodies that were made by someone else's body? Guaranteed everybody here has, because everybody here was born Everybody here was incubated in someone else's uterus at some point. Okay, so pregnancy is an example of that. The mother's antibodies cross the placenta, protect a developing fetus. Breastfeeding, for example, there are antibodies in breastfeeding, and they help protect the baby as well. Another example of this might be getting IgG shots to boost immunity if you've been exposed to something like malaria. Maybe I think it's malaria that they give IgG shots for. I'm not sure. But the point is that they're not your antibodies. They were made by somebody else. So it's passive. Your immune system doesn't remember how to make those antibodies that you got, from your mother's breast milk, for example. What we're going for the long haul is active immunity. Active immunity is when your body makes and remembers how to make the antibodies. When your body makes the antibodies. Go get your own antibodies. Go learn how to do it yourself. We want active immunity. Passive's great here and there, but eventually that kid's got to grow up. We all have to grow up someday and learn how to make our own antibodies. Darn it. That's a really great thing. And the nice thing is that it's very natural for the most part, Get exposed to life and you learn how to make antibodies to it. And also vaccination. Okay, so let's get rid of this screenshot. And we're going to talk a little bit. We got to get back to notability here. It always kind of wigs me out that the colors are different. Like, oh, I was drawing in purple back in notability. So here we are, we're back in purple. So a bit of history. Okay, humanity has been plagued by diseases caused by viruses, forever. And honestly, as long as there is human life here, there are going to be new viruses that we're going to have to learn how to deal with. And unfortunately, it seems to be that once every 100 years or so, we really struggle with this on a global scale. The last fully pandemic, was the flu pandemic of 1919? Was it 1919? Right around then. And here we are, 101 years later, dealing with the same thing again. But for most of From the time at which history has been recorded, humanity has been plagued by a disease called smallpox, which has been eradicated from the planet. Smallpox, it sounds like a small version of chickenpox. Okay, a pox is called blisters. Pox viruses cause blisters. Chickenpox causes blisters. Okay, chickenpox causes blisters. It can cause them all over your body. Smallpox was deadly, and the complications that resulted from it were harsh too, and people were very disfigured as well. Let's take a look at what smallpox looked like, because it wasn't eradicated until I think officially the late 1970s. So in my lifetime, there were still people getting smallpox, and we have Google that can show us images of what smallpox looks like. Yep, sorry if that trips you up a little bit, but yeah, we're talking really bad. People died of this. Much more than dying of chickenpox. So serious stuff. Now, back around the turn of the first century, like around the year 1000, we have evidence that in China, they used a particular technique called variolation. And I'll explain what that is in just a little bit. Unfortunately, they didn't didn't do a scientific testing for it, and somebody else has gotten credit for discovering variolation, but he didn't discover variolation. He just basically did actually a quite good test of this to show how it works. So he didn't, this dude I'm going to talk about did a little bit of science there and basically brought variolation to Europe and then to the New World, to the colonies, the American colonies. All right, so there was this dude back in like the late 1700s named Edward Jenner. Edward Jenner. And he was a country doctor. And he had actually heard rumors of this variolation thing because there were actually a couple of people from Britain who were like, hey, we heard about this variolation thing that's been going on in China. We're going to go to China and get this done. Well, can you imagine how much money that would take to be able to travel to China, sail around the Horn of Africa or, cross over Russia and the Ural Mountains and all that? So anyhow, Edward Jenner had heard tell of this. And he also noticed... Okay, so English country doctor, these words are going to sound really ridiculous. He noticed that there were milkmaids. I know this sounds like the 12 Days of Christmas song. Milkmaids. They are maids who milked cows. So these women who were milking cows, milkmaids, who caught a disease who caught an infection called cowpox from the cow. Milkmaids who caught cowpox from the cows tended not to get smallpox. They would get cowpox, which was a very mild infection. Mild infection, couple blisters, no big whoop. Smallpox, really, 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 really bad. Okay, so you'd much rather have cowpox than smallpox. And this guy noticed, maybe there's something to this thing that I heard rumors of, in the dark corners of the universe. That was 1796 or whatever. Noticed that they rarely, if ever, got smallpox. So he's like, you know what? I'm going to do me an experiment. I'm going to do a little experiment. I'm going to find a milkmaid with cowpox. And her name, this cracks me up, her name was Sarah Nelms. Sarah Nelms. Gosh, these names just sound so ridiculously British, like they need to be on the Great British Baking Show. Sarah Nelms is a milkmaid from Cornish. All right, so Sarah Nelms had cowpox. And he's like, you know what? I'm going to take her cowpox and I'm going to scrape up some of the pus from her blisters. This sounds so gross. Okay, here's Sarah Nelms. There's Sarah. Let's give her a little milkmaid hat, shall we? We'll give her a milk pail, too. Gosh. You guys are not going to miss me, are you? My stupid sense of humor. Oh, look, there's a milkmaid. All right, so she's got cowpox. I'm putting some pox on her. There we go. Edward Jenner is like, I'm going to take pus from one of these blisters. And I'm going to deliberately take that pus and find some kid whose parents say it's okay. He's not so sure about this. This is something the FDA wouldn't allow anymore, let me tell you. But I'm going to scratch this kid's arm and try to give him smallpox. And it's funny that so here's Sarah Nelms over here on the left. This kid is James Phipps. These names crack me up. Okay, so guess what? James Phipps gets cowpox. All right, so he gave somebody cowpox. That doesn't sound too horrible, but then he does something that would never be approved by the FDA anymore. At all. So he basically gave Phipps cowpox with pus from Sarah Nelm's cowpox. So he gets cowpox and recovers. Now dear James is happy, right? But then then Jenner is like, all right, now we got to challenge this. Now I'm going to scrape up pus. Yellow's not going to work. Pus from some random dude's smallpox blister. And now I'm going to inject that into James Phipps. I have no idea if there was any informed consent at all. But the good news is that dear James did not get smallpox. Let me just erase that. He does not get smallpox. So this is actually a pretty good, albeit no longer considered ethical, experiment here. He used pus from Sarah Nelms to give James Phipps cowpox, then takes pus from a smallpox blister and challenges James's immune system to see if it actually did remember, and James does not get smallpox. This is an early form of vaccination. And the names crack me up. Okay, so we have James Phipps, we have Sarah Nelms, we have Edward Jenner, and there's one more name I would be remiss in mentioning, and that would be that of the cow. Get the cow, its udder there. It looks like a dog head. Oh gosh, this is terrible. I don't know how to draw a cow. The ears are wrong. There's our cow. There we go. It's a Holstein. I don't know. The cow's name was Blossom. So Blossom gave cowpox to Sarah Nelms. They took Sarah Nelms' cowpox, gave it to James Phipps. He got cowpox. They challenged him and deliberately exposed him to smallpox, and he does not get smallpox. This is called variolation. It is not quite the same thing as vaccination. It's a very crude form of vaccination, isn't it? But let's think about the word vaccine and vaccination and where it comes from. And if anyone here speaks Spanish or Italian or Latin, what's the Spanish word for cow? It is vaca. Well, that's Latin for cow. Vaca is cow. And therefore we call this process vaccine comes from the root word for cow. So, if you're ever on Jeopardy, moment of silence for Alex Trebek. If you're ever on Jeopardy and that comes up, you'll know where the term vaccine comes from. Alrighty, so fast forward to the 1900s. We all remember them, I think. No, maybe we don't. Some of you were probably born after 2000. But let's talk about the early 1900s. There would often be epidemics, not pandemics, but epidemics of a disease called polio. You've probably all heard it. You've probably all been vaccinated for it. Polio. Polio was a nerve infection caused by poliovirus. By the poliovirus, of which there are several strains. So it's just like COVID is caused by the coronavirus, polio is caused by the poliomyelitis virus. And it was really a scourge. I mean, I think we all have a really good idea now of what it's like to be afraid of a virus and having it change our habits, right? It has changed all of our habits, whether you agree to them or not. We are required to wear masks indoors at stores, for example, or they're not going to let you in. We've all had to change our habits. The reason I'm talking to you here is because we had to change our habits at colleges and schools. We have to teach remotely right now. And it's not forever, but polio outbreaks caused a change in behavior in society as well. And probably none of us here are old enough to remember any of that. I'm probably the oldest of anyone listening to this now. I don't remember because the last outbreak was 1954. Polio was a mild infection for like 90% of the people who caught it, but for the 10% who weren't so lucky to have a mild infection, they developed paralysis. So paralysis of the leg because it gets into the nerve cells, and sometimes paralysis to the point where people had to be in an iron lung, which is this giant machine that pushes your chest cavity in and out to help you breathe because your lungs don't work properly anymore. Famously, an American president, FDR, Franklin Delano Roosevelt, developed a polio infection on Campobello Island in the 30s, I guess, during an outbreak there. It was contracted. It was not airborne, it was waterborne, and he was swimming in water that somehow was infected with it, and he was quite famously disabled and quite famously hid his disability from the American public because that was not an okay thing to be out in public about in the 40s. Anywho, where was I going with this? But back in the 50s, my mother would say, oh, no, I remember swimming pools being closed and lakes and beaches being closed because you could not swim. It traveled through the mouth and fecal route as well. So contaminated water, we have really good water treatment plants now, but, if water were contaminated at all, not properly treated, it would get into water. It could get into a large water reservoir, for example. So it was a big, hairy deal. And it was I'm trying to remember my dates here. But there was a huge push to develop a modern vaccine because we had this variolation thing here for smallpox, and we didn't have anything that worked for polio at all. But a researcher named Jonas Salk at the University of Pittsburgh, at the University of Pittsburgh Medical School, developed a vaccine, and I want to say it was actually released in, oh my gosh, let me see if I can find it. I should have had the internet open for this. I want to say it was like 1957. Not sure, but so late 50s, they released the first polio vaccine, and it was a game changer. So you know how excited we are now about the potential for not only one but two vaccines against coronavirus. There was so much rejoicing. I mean, Jonas Salk won the Nobel Prize for this. He also went on to form the Salk Institute for vaccine research. It's in La Jolla, California. Right. But he also started the a research institute at the University of Pittsburgh Medical School as well. But it was a game changer, and the first polio vaccine changed public health as we knew it, because vaccines are one of the biggest tools that we have in our public health toolbox. So we're going to be talking about the different types of vaccines that we have available to us. So first up, what is a vaccine? Okay, we talked about smallpox vaccination. It's really variolation. Vaccine, definition, preparation of a pathogen or its products that is used to induce active immunity. I want to add one little thing to this, so I'll take a screenshot here. A preparation of a pathogen or its parts that is used to induce active immunity. Active immunity where it gets your body to make its own antibodies against it. All right. So first up, let's talk about live attenuated vaccines. Sometimes this is called whole agent, or no, I take that back. I take that back. These are called live vaccines a lot of the time. This is where we give someone the virus, but it has been attenuated. This term attenuated means weakened, not weekend, as in Saturday and Sunday, but weakened. A live vaccine that is attenuated, it means the virus has been weakened to the point where it can still get inside your cells, but it can't cause disease. So here we go. I'm just writing this again, even though it's already written here. Patient is infected with a weakened form of the pathogen such that it does not result in disease. We're crossing this word generally out just because everything has a risk. And it's called a live vaccine because it's still the whole virus. I don't want you to think this is coronavirus because this is not what a coronavirus vaccine looks like. I'll just make this one look a little different. I'll put an icosahedral in here. There we go. Let's say this is infectious. This is the real thing. What we will do is either genetically engineer it or grow it in the laboratory under certain conditions so that it gets weakened. Or, better. I'm going to erase all this. Better. Oops. Like, let's say what it does, like it's still alive, it's still a virus. Viruses aren't alive, I know you know that. But maybe it does something to the little spike proteins that are on it to the point where it can't make you sick anymore. So it's attenuated. And here actually, or like messes up the protein code or something in there where it can't cause disease. Attenuated. Can't cause disease. Something like getting cowpox instead of smallpox, only even way less than that. Way less than that. Where maybe it just gives you the sniffles for a couple days or something like that. An example of a live attenuated vaccine is one that I have had. I'm going to delete that. And that is actually the oral polio vaccine, or OPV. This is not Jonas Salk's vaccine. This was made by a dude whose last name is Sabin. I don't remember their first name. But the oral polio vaccine came out a few years after the first polio vaccine, which we'll talk about in just a minute too. Oral polio vaccine, it's a live vaccine. Live vaccine. Oral, because they basically put a drop of it on to your mouth. And we gave that to children until 2000, the year 2000 here. So there might be many of you who have not had the oral polio vaccine. But that's one example of a live attenuated vaccine. All right, so attenuated vaccines, live vaccines, got some major advantages. There is a reason why live vaccines are basically the gold standard for vaccines, and that is because, okay, it does not reduce in disease, but one dose can induce immunity for a long time, for a lifetime sometimes. That is huge. That's huge. Getting a vaccine and having it last a lifetime. You don't need booster shots. If you've ever had a tetanus shot, you probably have. You got to get one of those every 10 years. Live vaccines, live attenuated, not so. They are the gold standard because they actually infect a person. They cause an infection, which doesn't make you sick. And by cause an infection, I mean they get inside your cells. You get a really strong immune response. The measles vaccine is an example of that. Is a live attenuated. And you get such a good response with that, which is a darn good thing because measles is wildly contagious. Let me think. Measles, the shingles, and the chickenpox, and the oral polio. Those are the only ones I can really think of right now. But the measles one, that is huge, and it is hugely effective. You don't need to get boosters for that at all. All right. Okay. Patient is infected with a weakened form, so it doesn't result in disease. One dose can induce immunity for a very long time. All right. A productive infection means a stronger immune response. Already said that. Now, this last bullet here is kind of interesting. Theoretically, because you actually get an infection, the fake measles virus, the attenuated measles virus gets inside your cells, technically you could, pass that on to someone else. Now, we have not seen evidence of this happening. Like, you could passively give the vaccine to someone else, but we have not really seen much evidence of this. But theoretically, it could be happening, And that would be quite an advantage, too. Okay, so attenuated live vaccines, pros, got those. Cons, because they are a live virus, they can mutate and become pathogenic and cause disease rarely, if ever. It's a very low risk, but it's a risk nonetheless. I do not know what the statistics are for the measles vaccine, like how many, does anyone ever get the measles from it? I know that it is very low, and I know I could go on and check on the World Health Organization's website to see what the current data is, because I will say that the CDC, the FDA, and the World Health Organization, when a vaccine has been created, once it's been approved and has been in use for a while, they don't just write it off, say, okay, that's one and done, we're done. No. they continue to monitor the effectiveness and any complications to a vaccine. They're constantly looking at the effectiveness and risks of every vaccine that's been approved. So they got our backs. It's not a one and done. They continue to look at those. All right. They can cause disease in immunocompromised patients and in fetuses. Pregnant women in general cannot receive a live vaccine because they can pass it on to a fetus. So if other patients who have certain autoimmune disorders or somehow immunocompromised based on medications that they have, or someone who has who has an HIV infection and has already shown signs of developing acquired immunodeficiency syndrome, they can't get live vaccines. And we'll talk a little bit about this later too, but when we discussed herd immunity, we want everyone, we don't just get vaccinated to protect ourselves. We vaccinate to protect an individual. I don't get a vaccine just to protect myself. I do it to protect the people around me too. People that I don't even know, people that I will run into in the grocery store who might be immunocompromised and therefore unable to receive a live vaccine, for example. So it's to protect others as well as to protect me, because some people cannot get certain vaccines. All right. This is kind of a wishy-washy downside, but because there are other vaccines that are not live vaccines that do require refrigeration, and we'll talk about that with the coronavirus vaccine later on as well. But most live vaccines all require refrigeration, which kind of might be a bit of a drag when it comes to trying to vaccinate, massive numbers of people all over the world, which is what we're going to be doing with the coronavirus vaccine, with the COVID vaccine. So this is kind of a downside, but other types of vaccines have that too. So can't really worry about that. Okay, so 2 general categories exist for vaccinations. Let's go with. We haven't done a different color for a while. Let's go with blue. In general, there are live attenuated versus all the other types of vaccines versus, let's say, inactivated. That's what your book categorizes them at, but I might actually have you watch This Week in Virology thing in which they don't categorize all vaccines as either live or dead, live or inactivated. But there are many different types of inactivated vaccines. The first of which is what we call inactive whole agent. And an example of this is the Salk polio vaccine. The Salk vaccine is an inactivated whole agent. So by whole agent, I mean the whole virus. But it's been inactivated to the point where not only does it not cause disease, it can't get inside your cells. So let's do a little graphic here, and I need other colors. Okay, whoa. Ooh, let's go with red, Dayglow red, and say, okay, here's a virus. Right there, and let's say it's got spike proteins here. Let's say this is live infectious virus, not live attenuated, but live infectious poliovirus. I don't even know what the poliovirus looks like, so I'm just drawing something here. We treat it in the laboratory in such a way, not grow it, but we treat it with chemicals, like it's often formaldehyde. Something that basically does a number on the vaccine, on the virus, so that it's intact. You still have the whole thing, but it's dead. Its spike proteins are like, something's happened to me. I'm all crappy now. Now I can't use my spike protein to bind to some receptor on this human cells. I'm dead. I am inactivated. It can't cause disease because it can't get inside your cells. BC, because it can't get inside your cells anymore. Which means it does not cause an infection. Not only does it not cause disease, it doesn't cause an infection. Whereas back here with the oral poliovirus, live attenuated, I've got to go back here. It still causes an infection. So here we go. This is what I want. Patient is infected with a pathogen such that it does not cause disease. Okay, so heck with this. I'm going to go back to my notability. Oh, God, stop. I'm pressing the wrong buttons here. Okay, inactivated can't cause disease because it can't get inside your cells anymore. It doesn't cause an infection. Live vaccines, live attenuated, cause an infection, but without the disease. So live attenuated causes an infection, but inactivated doesn't even cause an infection. Doesn't cause an infection. It's inactivated. It's like, so how come it still works if it doesn't cause an infection? Because there's still something about maybe this or something else that's on the envelope will still cause an immune response. Will still cause an immune response. But it does so without causing disease and without causing an infection. This is the Salk vaccine. This is the first modern vaccine that we had, and that we were able to develop a vaccination program to basically rid the world of polio. The world has not been completely rid of polio, however. There are some pockets of it. I believe the goal was to end polio, annihilate it by the year 2000. We did not. I think it was 2007 when it was nearly eradicated, but there are still some pockets of it now. Now let's look at the pluses and minuses, the pros and cons of an inactivated vaccine. Inactive whole agent. They don't cause an infection, so really low risk. Really, really low risk from the Salk inactive whole agent vaccine. Very low risk. You cannot get polio from the Salk vaccine. Usually they don't require refrigeration, but again, this is wishy-washy again, because some that are within this category actually will. It just depends on the preparation. And again, we'll talk about that in the next lecture. On the downside, protection doesn't last very long. So you generally need booster shots. So the Salk polio vaccine required some boosters, whereas the oral polio vaccine did not. So let's compare and contrast the pros and cons of inactive whole agent Salk vaccine to that of the attenuated Sabin oral polio vaccine. How might you decide which one to give to a community? It's, again, this is the debate we're having now about coronavirus vaccines, although I don't know if there is a live attenuated corona vaccine trial out there. I think actually there is not. But let's look at some pluses and minuses of the Salk versus the Sabin vaccine. All right, so Salk, which is inactive whole agent. And this one came out first, but just a couple years later, the Sabin oral polio vaccine came out, which is live attenuated. I misspelled attenuated. You got what I mean here. Okay, the Salk came out first, so yes, everyone in the late 50s got this right away. But, like, what do we do now? Salk is no risk, really. You cannot get polio from it. You might have some adverse reaction to something else that was in the vaccine, but it's low risk. Sabin is lower, is low risk. Now let's say slightly higher risk. Slightly higher risk. It's still low, but it's still slightly higher. That higher risk that the live vaccine could mutate and revert to its pathogenic form. Salk vaccine, though, because it's low risk, because it's an active whole agent, it's not as long lasting. Sabin vaccine could last a lifetime. I don't know the exact number of years they say, but I believe it's actually a lifetime. We do not get oral polio vaccines as adults anymore, unless you're going to go to a country where it might be prevalent. So what do? Which one do you want? Especially if you're working at the World Health Organization and you're trying to figure out a way to help everybody, not just you or your child, but the entire planet, and rid it, because that is going to help me and my family. Here's what we used to do for a while, and I think I got to research this because we may have gone back to this protocol for a while. And I know we have in certain parts of the world. All right, for a long time, we would just give the Salk first. To 1-year-olds. I forget what the vaccination schedule says to give polio, but I think it's right after DPT. So you give that first so that you have some immunity to it. And while you still have that immunity, you follow up later with the Sabin vaccine. So that just in case there were any risk with the live attenuated, you're protected by antibodies that your cells already made in response to the Salk vaccine. Now in the year 2000, I think because the prevalence of polio was so low then that we ceased to give the Sabin vaccine. That has turned out in several parts of the world to not be a great thing to only give the Salk vaccine, because here, for example, and I want to say the example that I read in your book was Israel. And I forget when, in the 90s or in the O's or even 10 years ago, everyone got only the Salk vaccine. So nobody got sick from it, but there was still a lot of live, real poliovirus around, and we want to get rid of it. We don't want it to have any human reservoirs anymore. Only Salk vaccine, so the real poliovirus stuck around, persisted. because it wasn't challenged by people who had long-lasting immunity from an actual infection from it. So I believe they actually started giving people the Salk vaccine as usual, and then the oral. So now it's Salk, then Sabin oral polio vaccine. These are the kinds of discussions that public health and epidemiologists have to have on a regular basis. Alrighty, so that's enough for now. Those are the basics of live attenuated vaccines versus inactivated whole agent. Next time, we will talk more about the other types of vaccines, and we will talk about the 2 coronavirus vaccines that are looking promising right about now, and we will look into vaccination programs and how that has to occur. Okay, everybody, let's finish up vaccines, and this will be our classes, the full class for the week of November 30th. Anyhow, we talked last time about the difference between whole agent, inactive whole agent vaccines, such as the Salk polio vaccine, and live attenuated vaccines, such as the Sabin oral polio virus. I should add that live vaccines are really like the gold standard because they just tend to grant long-lasting immunity. You get a much stronger, long-lasting immune response. And just to rehash a little bit, or to clarify a little bit about the concept of vaccinations, we are actually in chapter 18 right now. We're not in 15. I meant to tell you that last time too. We're in chapter 18, which is applications of the immune response. Now, your immune system reacts to molecules that are presented to it, molecules that are on a pathogen, for example. So, let's say, and the pathogen doesn't even have to be a virus, but let's say, let's say, yes, it's a virus. Let's put an envelope around the capsid and, maybe put a couple of some spike proteins and a matrix protein that holds that envelope together. There might be some other molecules here too. This would be, if we grew this in the lab and we grew it under conditions that allowed it to be attenuated, this would be, essentially a live vaccine. Your immune system sees this and goes, what the heck is this? What is this? This thing here, that's not self. This little molecule here is not self. These lipids here, this is not self. And so through a whole series of events, including antigen-presenting cells, your immune system eventually will make antibodies, and I'm abbreviating antibodies with ABS, will make antibodies against certain molecules, certain that we consider antigens, against certain molecules, aka antigens, that are a part of the pathogen. Okay, now the presence of antibodies is essential, but that's an oversimplification of developing immunity. You actually need a T cell response as well. And so with all the coronavirus vaccines that are currently in trials right now, they are looking not only to see if patients have made antibodies and prevent disease, they're also looking at a T cell response as well, specifically killer T cells as well. But we're focusing on antibodies because honestly, that is a major source of evidence that we have immunity. So for example, there are vaccines that are not as long-lasting, and we talked a little bit about that with the inactive whole agent. It's not as long-lasting a vaccine. There are some other ones such as the hepatitis B vaccine. It is not a live vaccine. It does not last forever. And so if you are a healthcare worker and constantly exposed to, potentially exposed to hepatitis, you have to, basically we say, we have to get your titers done. So you get your titers done. This means, do you still have antibodies against the hepatitis B virus? So it checks for presence of antibodies. So, and those of you who work in healthcare now, and I know a lot of you do, are well aware of this. You have to get your titers done every now and then. All right, so far we have talked about live attenuated vaccines and also inactivated. And just quickly, let's go back to, why did this go back to the first slide? Goodness. Sorry, don't mean to spin you around. I had the right slide all set up and it moved around. Okay, so we talked about live attenuated. Nope, I guess we gotta go, nope, it's forward. My bad. Here we go. There are different types of what we would categorize as an inactive vaccine. Okay, we already talked about inactive whole agent. I want to talk about these protein subunit, though. It's a subunit vaccine. And we'll go back to notability. Somebody decided, okay, so we've got this live vaccine up here, you know, but they carry a risk or something, and really we just need something that gets a good immune response. Do we really need this whole enchilada to stimulate immunity in the immune system? And the answer is oftentimes no. That you don't need the whole agent. Somebody had the idea saying, you know what, if we can get an immune response to, say, just this little spike protein here, why should we give the rest of this vaccine to everybody else? So somebody's like, hey, y'all, what if we make a vaccine that is basically just this piece here? Just a little part of the protein. So that would be a protein subunit vaccine. And the hepatitis B vaccine that I talked about actually is a protein subunit vaccine. So protein subunit is where just a piece of one of the viral or bacterial proteins, because not all vaccines are against viruses, they're also against some bacteria too. Protein subunit vaccines are when just a piece of the protein can stimulate immunity. Piece or subunit of a pathogen's protein is enough to stimulate an immune response. That is enough. And the hepatitis B vaccine is an example of that. I want to say Gardasil is, but I'm not so sure of that right now. Not 100% sure. All right. So there is protein subunit vaccines. There is also toxoid vaccines. Okay, this term oid here means similar to or like. So a toxoid is a molecule that looks like a toxin. But doesn't make you sick the way a toxin does. So it doesn't cause illness. But instead, like let's say a toxin is, like this molecule here. I don't know, I'm just making up shapes here, okay? I don't know what's possessing me to make a shape like this. I'm just making something up. Maybe that's the toxin, but maybe the toxoid looks like this. I'm just making up molecules with shapes here. Okay, maybe this shape here is enough to stimulate an immune response, but doesn't make you sick the way the real thing, the real toxin does. All right, an example of this is the diphtheria toxoid vaccine. There is the DPT vaccine, which is D is for diphtheria. This is a combination vaccine, tetanus and pertussis. Is it pertussis or pertussis? I'm not sure if that's an I or a U. I think that's another U. I don't know. Pertussis. But the D part, the diphtheria part of this combination vaccine is a toxoid vaccine. Toxoid. Yeah. Okay. There are polysaccharide vaccines. Polysaccharide vaccines are generally not given to children. So let's just screenshot this right here. All right. Let's see. Polysaccharide vaccines are when, and this is more for vaccines against bacteria rather than viruses. So usually against bacterial pathogens. All right, there is a meningococcal vaccine. Can I spell meningococcus? Meningococcal vaccine. Certain people are at risk for that. All right. So we have those. There's some, and pneumococcal vaccines that a lot of older adults will take. Pneumococcal. I can't spell pneumococcal either. All right, a conjugate vaccine. Conjugate, to conjugate means to get together, right? And a conjugate vaccine is basically a polysaccharide vaccine that's linked to a protein. Let's say attached to a protein. There have been some flu vaccines that have been conjugate vaccines. There are all different kinds of flu vaccines, though, so I don't want you to think that all flu vaccines are conjugate. No, they're actually not. A lot of them are protein subunits. Some of them are actually live vaccines. There are different ones. They change every year, and there are different choices that you have every year as well. But the conjugate vaccine, I believe the Hib is always Haemophilus influenza B. The Hib vaccine is a conjugate vaccine. Alrighty. Now the last one that I want to talk about is this messenger RNA vaccine. This is very new. If if the current, it's Pfizer and Moderna, I think, are the two SARS-CoV-2 vaccines that are messenger RNA vaccines. If either one of those, makes it through and it looks like it's going to happen, they will be the very first approved messenger RNA vaccine. So let's talk about how those work, what the deal is with that. All right, so let's get a different color here, shall we? I'm going to go back to purple. It's been a little while. So messenger RNA vaccines. Okay, now you already know the whole central dogma of biology is that, there's DNA and the gene is in the DNA and it gets transcribed into a copy, which is messenger RNA. Messenger RNA, which is the copy. And it's the copy, it's the messenger RNA that the ribosome reads. Oh, I'm going to draw a little ribosome here. Like it's, the 30S and the 50S ribosome. Well, that's bacteria. I guess in humans it would be the 40S and the 60S. So there we go. There's our little ribosome I decided to draw. And it builds a protein based on what that messenger RNA says. Okay, with RNA vaccines, it is the concept here is that we will introduce the body to the messenger RNA, to this little piece of viral RNA, and that your ribosomes, the ribosomes in your cells, will build basically the spike protein from that. I'll draw it like that. If we're talking that's the little spike protein on coronavirus. Like, let's draw a little coronavirus. What the heck? Y'all are going to get so tired of me drawing these viruses, aren't you? I'm going to put its messenger RNA in there. We'll keep it coated in purple. And I'll put the little spike proteins out here. Okay, now you know that it's the spike protein that allows the coronavirus to enter the cell. We've talked about that before. This thing right here. And so people are like, there is one vaccine, but it hasn't panned out, where someone's just like, well, why don't we just give the little spike protein to people, and their immune system will form antibodies against that. And that's definitely one idea, but the general idea with messenger RNA vaccines are like, okay, the messenger RNA here inside the coronavirus, and I'm up here in the upper right, so please be looking here since you can't see where I'm pointing to unless I'm drawing something. Right. The directions for how to make that spike protein are in the messenger RNA, right? Right in there. So this little piece of messenger RNA. So Pfizer and I believe it's Moderna, yes, Pfizer and Moderna are the ones that are working on these, are like, why don't we just package up the messenger RNA and give that to people as a vaccine? But the thing is, you can't just inject people with messenger RNA. RNA does not last very long. It will be broken down by RNases within minutes. Surely, it's just not long-lived in the cells. So they had to package it up in something, and they decided, well, we'll package it up in basically something that looks a little bit like a viral envelope. We'll package it up in lipids. And the lipid will protect it long enough for an immune response to fully develop. Now, I should add that this lipid coating is fragile. And with the Pfizer vaccine, it needs to be stored at -80. which is kind of a problem because a lot of hospitals, places that usually give out vaccines, your regular doctor's office, CVS and Walgreens, don't have freezers that go down to -80 to store all of these vaccines that need to be stored at that low of a temperature. -80s are actually very common in research laboratories. I mean, all the labs I worked in, we had several -80s because, it's really great long-term storage. But, CVS doesn't have those, and your regular doctor's office doesn't have them. So it's a little bit of a problem. It's definitely a disadvantage, but hey, we can do this. We can do this as a world and get everybody, all these places that need -80s, a -80. The Moderna vaccine, on the other hand, their little lipid vehicle for getting it into your cells, it only needs to be stored at, I believe it's -20. So stored at -20 degrees C, which is a typical usual freezer temperature. So this one is a little bit easier. Now, both of these vaccines have come out saying that Pfizer has said it's about a 90% efficacy. And I think Moderna came out and said that they're 94% efficacy. And when Moderna came out and said they're 94, Pfizer's like, oh, wait, we looked at our numbers and we're saying we're 94 as well. So we're the same. So yeah, we've got a little bit of a competition here. But the idea with their vaccines is that the messenger RNA gets inside your cells. Here, let's just draw it this way. Here we go. That it gets inside your cells. Let me draw the lipid thingy. And, here's your nucleus and all this other stuff. And we've got ribosomes in our cells here. That once inside the cell will break down that lipid and then translate the ribosomes of your cells will translate this into the little spike protein, and then the spike protein will stimulate an immune response. And it looks like that's really happening. So let's talk for a minute about what this 94% efficacy means. I'll just use the Pfizer vaccine as an example. Basically, they tested about 40,000 people. About 20,000 got the vaccine, and the other 20,000 got a placebo, a shot that just had some saline in it. So it wouldn't stimulate the immune system. And the people who got the vaccine and the people who got the placebo, nobody knew who was who. And this is after the vaccine has been tested for safety. And what they found, and basically they had to wait around for people to get sick to see who got sick. And they basically, I think they got only something like 100 cases? No, it must be something like 1,000 cases. But 90% of the people who developed COVID had the placebo. Does that make sense to you? 90% of all of the people out of the whole 40K, out of both groups, the group that got the vaccine and the group that got the placebo, 90% of the people who developed COVID symptoms had gotten the placebo, and only 10% had gotten the vaccine. So that's what this 90% efficacy means. And that is really, really excellent news. Now, there are a few questions about this that I and lots of other people have. Okay, for testing for COVID, 90% of the people who got COVID had the placebo. not all of these 40,000 people were tested for the virus, for presence of the virus afterwards. So the people who got COVID, this doesn't take into account anybody who was asymptomatic. So it doesn't account for asymptomatic cases. And we know there are a lot of asymptomatic cases. And what we don't know is maybe the people who got the vaccine, were they all asymptomatic? Were they still passing it on to other people? We don't know. And the other thing is, and this is less of a concern because the people who were selected for this vaccine trial were selected because they were probably at somewhat risk. They weren't people just totally staying home. Part of but still, is it like, well, if not a lot of people got sick out of this whole 40,000, is it because they were all staying home, working from home, and never went anywhere anyway? That's definitely a possibility, but I would say that from what I have read about how Moderna and Pfizer and all of these companies, all these pharmaceutical companies working on a COVID vaccine is that they are looking for people who do not work at home, who have to be out and about to work. So they were trying to select for people who, regardless of whether or not they got a vaccine or a placebo or even participated in the trial, we're going to be out in public. We're going to be working around other people, so that they could say, that it's probable that they have been exposed and they still didn't get sick. So this is good news. This is good news. The only major concern that I have, and that I've read about other epidemiologists have is that this still doesn't account for any asymptomatic cases. So we'll see, but it's very, very good news. And Moderna had a similar thing going on here too. So yeah, they just had like a 94% efficacy. One more thing, this term efficacy, this refers to how well it worked in the vaccine trial. It's not the same as effectiveness. Efficacy does not equal effectiveness. Excuse me. If a vaccine has 90% effectiveness, this refers to how well it works out in the real world. Oops. Got one of my notifications coming in. Okay, so that's the reason that they're using the term efficacy as opposed to effectiveness, because efficacy is how well something works in the trial. When it gets out into the real world, we'll see. Because then, you can't hide asymptomatic cases. Let's see, so we've got that. Yeah, and then finally, what I really need to say about about both vaccines or any of them is that I read a quote, it was from some infectious disease expert who said vaccines don't save lives, vaccine programs do. Vaccine distribution programs are what saves lives. And their point was like, well, okay, vaccines actually do save lives, but they don't save lives unless you get the vaccine, right? So it's really vaccination distribution programs. Save lives. So that's why it's a major deal trying to work out how to get this vaccine out to everyone, how to get it to the riskiest populations first, and until we can basically get up to 90% percentile of the population, so that then we can develop true herd immunity. So that's the deal there. I read in the paper this morning, actually, that Operation Warp Speed is going to be getting ready to set up the largest population areas to get the vaccine first. And that is a bit of a departure. Usually we really have to get it out to the most at-risk populations first, but we'll see. We'll see how that works. I read a little bit, I read a couple of misconceptions about herd immunity in your assignment for when you listened to the This Week in Virology podcast. And I just want to reiterate, herd immunity is the minimum percentage of the population that has to be somehow immune to a disease in order to protect everybody. The minimum percentage of a population that must be immune to a disease either through vaccination or immunity that persists from having had the infection this is getting to be a long definition here. The minimum percentage of a population that must be immune to a disease, either through vaccination or immunity that persists from having had the infection, in order to lower the incidence of the disease, or rather in order to lower the incidence of a disease, to eradicate it and to protect those who can't be vaccinated. So to eradicate the disease and or protect those who can't be vaccinated. And those who can't be vaccinated, people who are immunocompromised, who have autoimmune disorders, who pregnant women, for example. So it's not only vaccination, but but you require some sort of immunity that either usually comes from vaccination, but immunity can persist from having had the infection. The problem with developing herd immunity for COVID is that immunity does not seem to persist very long. There's a lot of evidence showing that antibodies only last about 4 months. I mean, we're talking immunity that has to last many years. So long-term immunity that persists from having had the infection, and that's kind of wishy-washy. Doesn't happen that often. So this part here that I've underlined here, it's uncommon. It's uncommon, so you really need it through vaccination. So that's why that whole Great Barrington thing was just never going to work. Like, hey, let's just let everybody get sick from it, and then we'll all be immune to it, and we can all go back to our lives. But the thing is that immunity doesn't even last that long. We don't know how long that immunity even lasts, and that doesn't even take into the account the horrible outcome that millions of people would die from this. I mean, we're already well over 200,000 deaths from this in this country, and I certainly don't want that to be. I don't want to be one of them, and I don't want any of you to be one of them, or anybody I care about to be one of them. So that's why that whole Great Barrington thing is just Not going to work. We have, take home message, we have to get a vaccine, and we have to get it, we have to distribute it in the most efficient way possible. Right. So let's see, we have talked about inactive whole agent vaccines, protein subunit vaccines, toxoid, polysaccharide vaccines, conjugate vaccines, messenger RNA vaccines. All of these here are inactivated vaccines, and they all have low risk. They cannot cause an infection because it's not a whole live virus. Only a live virus can cause an actual infection. So all these babies here, they are low risk vaccines. We already talked about how don't usually require refrigeration. Don't usually, but these two messenger RNA ones definitely will. So that's not really much of a pro anymore for inactivated vaccines. Protection does not tend to last as long. You often need booster shots. And as far as booster shots for the new COVID vaccines, we'll see. People have to be monitored to see how long their antibodies persist. So that will be an ongoing sort of thing. All right, we talked about this already. Let's talk about vaccine safety. Okay, we've already talked about herd immunity. Only works if a high percentage of the population is vaccinated. For something like measles, which is wildly contagious, you need something like 97% of the population to be vaccinated against measles in order to reduce incidence of those. I'm well aware of anti-vax rhetoric that has been around here. I have friends who still think that vaccines cause autism. They don't. They don't, and that has been shown time and time again. The person who published this, Andrew Wakefield, falsified his data. He lost his medical license in Great Britain as a result. He was paid to do this, falsified his data for 11 patients that were in this quote-unquote study of his. However, that is not to say that vaccines are without risk, because all medical procedures do carry a risk, and one of the biggest ones are adverse reactions to other ingredients in the vaccines. Okay, so for example, egg allergies. People with an egg allergy cannot have a vaccine that has been grown in fertilized chicken eggs. A lot of live vaccines are actually grown that way, because a virus, to make more of a virus, it has to infect a cell. They actually use chicken eggs for that. If you've got an egg allergy, can't have that. Let's see. There is a class of molecules that I should talk about called adjuvants. Why did I do that? I didn't need to take another screenshot there. Adjuvants. Adjuvants are molecules that are added to vaccines to enhance the immune response. When modern vaccines were first developed in the 50s and early 60s, different companies were producing them, and there were certain companies that were like, okay, we're going to scrub out all of the vats and everything and all the containers that we keep everything in. We're going to keep everything really super, super clean. And the things that were kept super, super clean in a certain way actually ended up producing a less effective vaccine, that there were actually some substances that needed to be in them that, I don't want to use the term dirty, that made them a little dirty, but it removed substances that were getting into the vaccines that actually enhanced the vaccine's immune response. A lot of these are aluminum salts. And also, I mean, now everything is very, very controlled, and these are deliberately added. Squalene compounds are often added, and what they do is they trigger a more intense inflammatory response in the area of the injection. So you get a stronger inflammatory response at injection, and that stimulates a stronger full immune response. There we go. So adjuvants are deliberately added to vaccines. They are substances that are not intended to have antibodies made against them, but they intensify the inflammatory response and basically call the rest of the immune system on over to that injection site. They are very carefully added now. It is not a haphazard thing as when they were first discovered, basically. And they have been well studied. A lot of anti-vaxxers who still think that vaccines cause autism are in response to a substance called thimerosal. It's a mercury-containing. Sorry, that's magnesium. Hg is mercury containing. Substance that actually used to be a part of some live attenuated vaccine preparations. Emphasis on used to. And this is it's just trace amounts of mercury, but it used to be a part of some live vaccines, but thimerosal has been out of use for quite some time now, like 30 years, so it's not in. I think there's only one vaccine that I think it might be in, but they even took that out a while back too, so it's very, very uncommon, not used anymore, except for maybe one type of the live flu vaccine. But so people who are saying vaccines cause autism because they have thimerosal in them, you can just look at it pretty easily and say, nope, this one does not have it. So I'm going to leave it there, and this will be enough for the week between this lecture. I put just one really large lecture together, and no, I did not expect you to listen to the whole thing all at once, but this will be enough just for the week. I'm trying to just do one upload this week and make it a little longer than usual. I will see you next time, and I hope you have a safe week, and we'll talk in Zoom. Be well.